Hi, here we have a video on group 2 compounds this time, and what we're going to cover is we're going to cover their reactions with water. Then we're going to have a look at the solubility of the hydroxides, that is the compound that is made when they do react with water. And we're also going to have a look at the solubility of the sulfates, so group 2 sulfates. And extraction of titanium is relevant to group 2 compounds because magnesium is used. And lastly, a few other uses of group 2 metals and compounds. And as we start, you may be wondering why we've got a picture of a hand grenade here on the right hand side, and that's one use that we won't cover in any more detail of a group 2 compound. Barium nitrate is mixed with thermite. You might have seen the thermite reaction in GCSE chemistry. So that mixture is very explosive, and that's the explosive that's used in these hand grenades. Anyway, let's crack on with the reactions with water. So when group 2 elements react with water, they form 2+ ions. All right, and so the ionic equation for that is the group 2 atom is going to turn into a 2+ ion, and in the process give up 2 electrons. So, for example, if we were considering calcium, calcium would turn into a calcium 2+ ion and give up its 2 outer electrons. And that's what happens with all of the group 2 elements, of course. So when the reaction happens with water, and you start off with calcium solid, and you react it with water, you're going to get calcium hydroxide, and you're going to need 2 hydroxides because each hydroxide ion, you might remember, has a 1- charge, and the calcium ion has a 2+ charge, so you need 2 minuses to cancel the 2 pluses. And you're also going to get hydrogen gas given off. So you can judge the speed of the reaction by the amount of hydrogen gas that's coming off, if you want, or alternatively, if you wanted to judge the reaction, you could measure the pH and see how many hydroxide ions are being created in this reaction. But first of all, let's consider the theory of the reaction rate. In the previous video, you may remember, we looked at the energy that was required to make these group 2 2+ ions, and we saw the downward trend in energy. So the amount of energy required to remove the 2 electrons is less for barium, for example, than for beryllium. And so what that means is the reactivity of barium with water is going to be much faster than the reaction of beryllium with water, because it just takes too much energy to remove beryllium's 2 electrons. That's in effect the activation energy of the reaction. That barrier is too high, and so the reaction doesn't happen. So if you were to dunk some beryllium into some water, you would find that it doesn't react. So it doesn't react, and magnesium only reacts slowly, let's say very slow. Calcium, on the hand, is, let's call it a steady reaction. Strontium is getting fairly quick. And by the time you get to barium, barium is a rapid reaction. And that's all because of this activation energy is less, because it takes less energy to remove those 2 electrons to make the ions that would react with the water molecules. Okay, and if you did want to make magnesium react with water, here is how you might do it. We've got some equipment here. On the left hand side you can see there's a test tube and a clamp, and we've got some magnesium down here, and here we've got some wool, and it's been soaked in water. It's been soaked in water, that's going to provide the water that reacts with the magnesium. But we're going to turn it into steam by heating it, and we also have to heat the magnesium if we want it to react. All right, so then we would have it react, and it would react and turn into magnesium hydroxide. The magnesium hydroxide would stay here because it would be a solid. But the hydrogen gas that is evolved would come down our delivery tube, and we could collect it underwater like here, and you'd have some hydrogen gas. And you probably remember the squeaky pop test that we might do with that to prove it was hydrogen. So that's the sort of experiment you would do if you wanted to make magnesium react with steam. We might do that in class. But as it happens, that's it for the reactivity of group 2 metals with water. What we're going to do now is study their hydroxides a little bit. Okay, and the aspect of the group 2 hydroxides that we're interested in here is their solubility. So let's just unpick a couple of the words here. Group 2 hydroxide, so we mean, for example, magnesium hydroxide, like so, or calcium hydroxide. Be the same format of formula. So the hydroxide ion is a 1- ion, so you need 2 of them to neutralize the 2+ group 2 ion. So we're talking about the hydroxides like those two and the others, and we're interested in their relative solubility. So let's just investigate that word solubility. And subjectively, we can use 3 different terms to differentiate different solubilities. We can say something is insoluble. And if we say it is insoluble, that means that the solute, the thing that's dissolving, doesn't dissolve at all. None of it makes it into aqueous solution. Or if a little bit of the solute does dissolve, then we can call it sparingly soluble. And if a fair bit of it dissolves, then you just call it soluble. They're not quantitative measurements, they're subjective, as I said, and also depends on things like temperature of the solvent as well. So, but they are often used in subjective way to describe solubility of various compounds. So let's just have a quick look at the reaction, what happens. So when magnesium hydroxide, for example, dissolves in water, so we're going to have solid magnesium hydroxide, and you're going to add it to water. If it dissolves, which in this case it doesn't do very much of, you're going to get magnesium ions in aqueous solution, floating around in the water, surrounded by water molecules, and you're also going to get hydroxide ions. And let's just balance it while we're at it. Also floating around in aqueous solution. So it would become alkaline. The pH would increase. The pH of aqueous would be 7, and the pH of this solution would be greater than 7. It would be alkaline. So that's what happens. We could also investigate the solubilities by starting off with the ions. Alright, so starting off with the ions, so you'd have a solution of a salt that was very soluble, and you might add some sodium hydroxide to it. Alright, so you're actually adding hydroxide ions by means of sodium hydroxide, and you could say that you could observe whether you get a precipitate. Right, so you might make magnesium hydroxide precipitate, and you could see how much precipitate you get. Or you could, if you don't get the precipitate, it means the magnesium hydroxide would be aqueous, right? And so the relative amounts of the precipitate versus what dissolves could give you an idea of the solubility. And if you did that in lab, you would get results such as this. We've got a chart here. So we've got magnesium ions added to sodium hydroxide. We're going to do the same with calcium and strontium and barium. And if you were to do that, these are the observations you would get in this middle column here. And with magnesium ions, when you add hydroxide to it, you would see a thick white precipitate. That would be magnesium hydroxide, of course. And that would look as if magnesium hydroxide was actually insoluble, right? You wouldn't observe any of that precipitate dissolving. And you might quite easily say that it's insoluble, but if you were to check the pH of that solution, you would find it slightly alkalinic, which means that there were some hydroxide ions created, which means that it did dissolve a little bit. So we're going to call this sparingly soluble. And you can see that you get a white precipitate of calcium hydroxide, and then when you do the same with strontium, you get a thin white precipitate. All right, so the white precipitate of calcium hydroxide was less precipitate being formed than with magnesium, and less still again with strontium, and we can call that a thin white precipitate. So it's like there's less of the precipitate in the liquid, the clear liquid, so it looks thinner. And when you get down to barium, it looks very thin, which means most of it is dissolved. Okay, so from those observations, those visual clues, we can see that the solubility, right, of those hydroxide increases because we're getting less precipitate formed. More of the precipitate is dissolved. So that's our major conclusion. We get the solubility of hydroxide increases as you go down the group. In year 12, you don't need to understand why. We'll have a look at those solubility trends again in year 13 when we do thermodynamics. But for now, you just need to remember that that's the trend. The solubility of the hydroxides, the group 2 hydroxide, increases as you go down the group. And in quantitative terms, we can see the numbers here. So magnesium hydroxide has a low solubility of 0.014 grams per 100 cm cubed of water at a particular temperature. And that increases down the group as we observed visually with the previous experiment until you get to barium hydroxide, which is quite soluble. So sometimes calcium hydroxide is termed as soluble. Some of the observers might say that 0.173 grams per 100 cm cubed was still sparingly soluble. But these definitely would be described as soluble using our subjective terms, whereas magnesium hydroxide would be termed definitely as sparingly soluble. What you might want to do on your own is to convert these solubilities, this unit of solubility, which is grams per 100 cm cubed, into moles per decimeter cubed. I think you know how to do that. If you did that, what you would find is the solubility of calcium hydroxide is about 0.01 moles per dm cubed, whereas barium hydroxide, for example, is about 0.1 moles per dm cubed. Lastly, let's just think about this solubility measure again. This is the maximum amount of solute. These are the solutes here, the solid hydroxides. So the solubility, when we're measuring like this, is the maximum amount that dissolves. So if you added any more than 3.89 grams of barium hydroxide into 100 cm cubed of water, if you added any more than that, then it wouldn't dissolve. So this is the maximum amount of barium hydroxide in grams per 100 cm cubed of water that would dissolve. And so that's how we measure quantitatively solubilities. While we're talking about hydroxides, let's mention a few of the uses of the group 2 hydroxides. And they generally rely on the alkalinity, the fact that we've got OH minus ions that we can use to neutralize acids when we want to do so. Okay, we're going to have a look at, first of all, magnesium hydroxide. All right, so this product is called milk and magnesium. It's a product that you might take if you've got indigestion. and so it's just a suspension because magnesium hydroxide is not very soluble. You remember it's sparingly soluble. So it's a suspension of magnesium hydroxide, and you take it for indigestion, and indigestion happens when your digestive system gets too acidic. Normally your stomach acids are 0.1 mole per dm cubed hydrochloric acid, which is pH 1. If they get more concentrated than that, then you start to feel uncomfortable, and so you can take some milk of magnesia or magnesium hydroxide in order to neutralize those acids. So that reaction would be magnesium hydroxide plus our HCl, and that would give us magnesium chloride and water. Standard alkali plus acid gives us salt plus water reaction. And so as you can see, we've used the alkalinity of magnesium hydroxide to neutralize an unwanted excess of acid, in this case hydrochloric acid, to make a harmless salt and water. So that's one use of magnesium hydroxide. Here we've got some garden lime and a tractor spraying it onto a field. So when you get acidic rain, and that rains onto the soil, the water in the soil is a bit acidic for the plants. Plants like a pH of about 6 to 7. Most plants like a pH of 6 to 7 to grow at optimum yield. If that is a lower number than 6, then you're not going to get much crop, and so the farmers will want to neutralize those acidic parts to the soil. It's not just acid rain that makes the soil acidic. Sometimes if there's a lot of aluminium in the ground, then that leads to acid as well. And so here we're using calcium hydroxide. All right, so this stuff here is going to be calcium hydroxide, and we've got a similar reaction that happens. It can either be sprayed on as a liquid or it can be put on as a solid, and then when the rain dissolves it, then it neutralizes any acidic water in the soil. Okay, so that's a second use, using the neutralization reaction of calcium hydroxide. We'll look at one more. You might have seen this before. So flue gases from power stations, for example, when they use fossil fuels, will, as well as making carbon dioxide and water vapor, they're also sometimes going to give off sulfur dioxide, especially if there's a lot of sulfur in the fossil fuel, which there is in coal, for example. So coal-fired power stations would need this particularly importantly. So if you've got sulfur dioxide in your flue gases, and that eventually reacts with the water that's in the atmosphere or the steam of the flue, then you're going to make eventually sulfuric acid or sulfurous acid. You actually make H2SO3 sulfurous acid, and that sometimes also gets converted into sulfuric acid, which is one of the acids in acid rain. So you don't want that sulfur dioxide to get out. So what you do is you use, actually in this case, usually calcium oxide is used, and that's made into a slurry by mixing it with water, and the gases pass through that slurry, and the calcium oxide reacts with the sulfur dioxide and eventually turns into calcium sulfate, so that sulfur dioxide is not getting out into the atmosphere. Okay, so there we have three uses of, well, in fact 2 uses of hydroxides and 1 use of calcium oxide, but all of them use the neutralization reactions. Now we're going to switch to the sulfates, the group 2 sulfates. So let's just write out the formula of one of these. So calcium the sulfate ion, as you know, is SO4. That's a 2- ion, and so that would be a formula of a group 2 sulfate. And when we look at their solubilities, we see that in contrast to the hydroxides, the solubilities decrease down the group. So magnesium hydroxide, for example, is going to be much more soluble than barium hydroxide. So if we did a little experiment, a similar experiment to the one that we did with the hydroxides, starting off with the group 2 metal ions, i.e. a very soluble solution of the ions, and we added sodium sulfate, for example. So we're going to create a reaction where the group 2 ion reacts with the sulfate and either dissolves or forms a precipitate. And if we did that, this is what we would see. So we started off with the ion, we added sodium sulfate, and the reaction that you might get here would be the Mg2 plus from the original solution. It reacts with the sulfate ion. All right, and that's going to make magnesium sulfate, but in magnesium's case that would stay in aqueous solution because you're not getting any precipitate, whereas if you did that for barium, for example, you're adding your barium ions that are in solution, might be barium chloride, for example, and you add your sulfate ions from the sodium sulfate, and you're going to get barium sulfate, and that would be a solid, and it would come out as a thick white precipitate. So this is really not a correct ionic equation because it stays aqueous, whereas this is a correct ionic equation because we've got a change of state. These are aqueous, right, and we've got a change of state to solid, so it's correct to write it like that. But anyway, we're doing this to illustrate the solubilities, and we can see that magnesium hydroxide is soluble, and we might call these two sparingly soluble. Whereas this is insoluble. Barium sulfate is insoluble. And so in terms of the trend, you can see the trend here. The solubility increases as you go from the bottom to the top of the group, or as the title suggests, decreases as you go down the group. And again, you don't need to know why at this stage. You just need to remember that that's the trend, and it's opposite to the trend of hydroxides. Okay, so what we can do is we can discuss a use for this chemical phenomena, in particular the use of barium, and the fact that barium sulfate is insoluble. It can be used as a test for sulfate ions. So let's talk about this test tube here first. Let's say you've got in here. Let's say you've got the unknown chemical. You think it might contain a sulfate. You suspect that it might contain a sulfate. And so what you do is you're going to add to it from here. You're going to add to it a few drops of barium chloride. So barium chloride is soluble and makes a solution, and you add those drops, and what you're going to find is if it does contain, if your unknown substance does contain sulfate, you're going to get a reaction where you make barium. You're going to make barium sulfate. And barium sulfate is insoluble, so you will see that as a precipitate. So you would see that as a precipitate, and then you would know that the unknown substance did contain sulfates. If you saw no precipitate there would be no sulfate in that unknown substance. This is what it looks like in a real picture. So you've added your drops of barium chloride, and as soon as the barium chloride reacts with the As soon as the barium ions in the barium chloride react with the sulfate ions that were in the solution originally, you can see them come off as white precipitate. So this is our barium sulfate precipitate. Now, another use of group 2 compounds is that of barium meals. Now, barium compounds are very poisonous, but for barium sulfate, because it's insoluble, completely insoluble, if you were to eat some barium sulfate, it wouldn't be dissolved by any of the water in your body, and it would pass straight through your body. All right, and that's quite useful. Right, so barium meals are used to investigate intestines because the barium sulfate will block X-rays. They will absorb X-rays, and so normally X-rays pass through the body, like so, such that when it's going through the flesh, the X-rays go straight through, and when it's going through the bone, they get absorbed a bit, and so you can see the bones. But if you're actually interested in looking at your intestines, that's no use. So what you do is you eat a barium meal. The barium sulfate coats your intestines, and so when you shine X-rays on your intestines, you can see them in the X-ray, like so. Okay, so here we can see a large intestine, colon, and that's probably a problem there. So as well as being able to see the bones, you can now see the intestines, and that's a major use of barium sulfate. Okay, now we're going to have a look at one of the uses of magnesium metal, and that is in the production of a different metal, titanium. Alright, so magnesium metal is used in the extraction of titanium, titanium being a very useful metal. For example, it's used in jet engine turbines and also in replacement hips. And the reason why titanium is used in applications such as this is that it has very high tensile strength. It has very high tensile strength, similar to that of steel, and yet it is uncorrosive. It's uncorrosive because it quickly forms a layer of titanium oxide on the outside, which is completely unreactive. It means that more oxygen can't react with the metal inside. So it's uncorrosive, and it's also light, because its density is about half that of steel. So for those three reasons, it is better than steel, and yet it's much more expensive than steel because of the extraction process. The problem is the ore exists. Let's change color. Let's do. The ore exists as titanium oxide, TiO2, and it's difficult to extract directly the titanium from the ore, the titanium oxide. If you try and reduce with carbon, then the titanium you get is brittle, because there's still some carbon in the titanium, and so that's essentially titanium carbide, and that's very brittle, and so we can't do that. And if you reduce it with other reactive metals, I don't know, let's say sodium, then you get impurities that are difficult to remove. So what you have to do is you have to do a two-step process. It's called the Kroll process, K-R-O-L-L, which necessitates first making the titanium oxide into titanium chloride in a reaction such as this. So you've got your titanium oxide plus your chlorine, and you're going to make that into TiCl4. And you're going to get some carbon left off, and also some carbon monoxide. Let's just balance that, like so. But the important product is this TiCl4, which interestingly is a molecule. And at room temperature it's a liquid, but when we want to use it in the reaction, we make it into a gas, and then it's produced. It's used in a displacement reaction in equipment such as this, where we also use the magnesium. So here's the magnesium, all right, and here's our titanium chloride. Here's our titanium chloride, and what we want is the titanium from it. We want this titanium, and so that necessitates a separate reaction where the magnesium displaces the titanium, goes off with the chlorine, and leaves the titanium as a metal. So that's the reaction here. We've got titanium chloride that we've made, and we've put that into a gas format, right? And you add some magnesium to it. You have to liquefy the magnesium first, and then you get this displacement reaction where the titanium comes off as a metal, all right, a liquid at this temperature, right? And you've also got your ionic magnesium chloride. And you have to do that as a batch process, and the fact that it's a two-step process like that also makes it very expensive. So you can see that it's expensive, but because of its excellent advantages, like its tensile strength, like the titanium's tensile strength and uncorrosivity and its lightness, then for certain applications it's worth it. Okay, that wraps up our video lesson. Let's just check that we've done everything we said we were going to do. So we've looked at the reactions with water to make hydroxides, and we've looked at the solubility of those hydroxides and the trend in the group. We've also looked at the opposite trend of the sulfates, and we've looked at the extraction of titanium by producing titanium chloride. And lastly, we looked at several uses of the group 2 metals, like magnesium, used in the extraction of titanium, and the compounds like magnesium and calcium hydroxide, barium sulfate, and calcium oxide. All right, so we've done quite a few uses as well. I hope that's been clear.